So our second change maker of the evening is Zhen Yin from the PhD student in the Department of Mechanical Engineering, working with Professor François Barthelat in the Laboratory for Advanced Materials and Bioinspiration. Nature creates extremely strong materials like teeth and bones and seashells out of the relatively weak raw ingredients that it has to work with. And so Jen's going to tell us how we can take inspiration from nature to use low value and low quality materials like recycled plastics and glass in order to make sustainable materials that have very strong engineering properties. Jen.
Thank you. Good evening, everyone. So, what kind of waste materials we are talking about here? We all know plastic waste. They are in every corner of our life. Plastic bags, plastic bottles. They are hard to degrade and hard to dispose without further pollution. Construction waste is another kind of wasted materials that has become a big problem in many fast-developing countries. And also, right here, right now, in Montreal, near our campus. Recycled materials, you may be surprised that I also consider it as one of the wasted materials. Why? Because recycled materials usually have inferior properties to its original materials, as it will be too expensive to regain its original properties. So usually, they can only be used in low-value applications, like building a desk or building a table. If left untreated, considering the amount of wasted materials we produce every year, we may be buried by those wasted materials eventually. So what do we do with them? Honestly, our current efforts to deal with those wasted materials are not very efficient. Take plastic waste as an example. We try to use biodegradable plastics, but are they really degradable? They can be degraded to small pieces, but those small pieces can no longer further degrade. For construction waste, it's pretty much the same story. For recycled waste, recycled materials, as I mentioned, they can only be used in low-value applications for their inferior properties. It is interesting that we always view them as useless materials. But what if we can view them from another perspective? What if we can turn those wasted materials into materials that are being useful in high-value applications? It would be great to do so, but the question is how we do that. I think I can give some few hints here. We can start thinking from the features of those wasted materials. For plastic waste, they're usually very ductile, but they are low on strength and stiffness. For construction waste, usually they are ceramics, bricks, or rubbles. They are relatively stiff and strong, but they are low on toughness, which means they are very brittle. And so ductile, but weak. Stiff, but brittle. Neither of those features are great for engineering applications. So who can make great materials from ingredients that have such features? Nature does. Many biological materials are super tough bioceramics that can be made of weak constituents, such as weak proteins and very brittle minerals, which were used to make chalks, and you know how fragile they are. Those biological ceramics achieve a toughness 3,000 times higher than its weak ingredients. And to keep it in mind, those ingredients are actually even weaker than the wasted materials I just mentioned. Another thing interesting to mention is that when biological systems create those materials, there's no pollution and low energy cost. As biological systems just recycle everything they need from other animals or from nature itself. Nothing will be wasted in our Mother Nature. Not only biological materials amplify the toughness, they also have balanced material properties which are usually mutually exclusive in traditional engineering materials, like stiffness and toughness. If we can learn from those biological materials, we may design new, novel bioinspired materials that can be also made of weak constituents and it has high performance. But first of all, we need to know how biological materials works. To understand how biological material works, we need to first zoom in. In the microscope, unlike most of the engineering materials, biological materials has complex yet highly controlled microarchitectures. Each biological materials may have its own way of those architectures, but they do share some common features. Take seashells as an example. Usually, they are made of stiff yet brittle mineral tablets, and organic interface, which is ductile as the adhesive. So from this, we know that we can, this is more or less like linear and brick motors, like what we do in the traditional architectures. So the next step, I would like to introduce the concept of architectural materials. As we all know, biological materials are kind of architectural materials. Architectural materials is a kind of material made of 2 or more ingredients with dissimilar properties. And for example, if we have a very stiff material and another material which is very ductile. So neither of them are great for engineering applications because they don't have very balanced properties and low toughness. Traditionally, we can laminate them, which is the working model and the loose model. But still, they are either stiff or very ductile. So for architectural materials, we combine those 2 materials into a sophisticated but well-controlled architectures. Therefore, we have balanced properties between stiffness, strength, and ductility. Therefore, we have a well-amplified toughness, which is energy dissipation. So biological materials is actually a very successful materials through billions of years of evolution. It provides great templates for us to design new bio-inspired architectural materials. But it will be not enough to just copy everything from nature because they use different kind of materials that we are dealing with. So we need to understand the mechanism behind those architectures. So I think we can conclude 2 basic guidelines from those biological materials. First, we need to exploit the full potential of each ingredient in these architectures. Second, by using those architectures, we need to let more and more contents of materials to get involved in the energy dissipation procedure. And all those ingredients should work together. Using nacre, which is the inner layer of abalone shell, as an example. Nacre is one of the toughest biological materials in the world. Usually, the brittle and stiff mineral tablets, they prevent strength and bridging the crack from its further propagation. And the sliding between the tablets also makes sure that all the organic interface are deformed in shear, which is their favorable way of deform. The interlocking between the tablets also makes sure that more and more volume of the materials will be involved in the deformation process, which means amplified energy absorption. And the shear deformation of those organic interface also relax the stress within the tablet and thus prevent it from breaking. And the weak interfaces also create a pathway for the crack to deflect, which prevents the catastrophic failure of the material. So by understanding all those mechanisms, we know that all those mechanisms contribute to the amplified toughness and balanced properties of the materials. But how can we implement them into the design of our new materials? I think our research proved the concept that we can indeed using bioinspiration and the concept of architectural materials to turn inferior materials into high value and superior materials. For traditional engineering materials, indeed, they are high in mechanical performance. But in the meantime, when we manufacture them, they produce a lot of energy consumption. And for recycled materials and waste materials, we don't need any energy to create them. They are already there. But the problem is they have inferior properties because most of the time, we just mix them together, so they don't have good properties. And thus, they can only be used in building a desk or building a tables. And we have to build that table very thick because they have inferior properties. Using the concept of bioinspiration, we can create architectures within those inferior materials. Therefore, we have an enhanced version of them, and we can have materials has as good performance as those traditional engineering materials, or even better. And in the meantime, we keep the energy cost low. Our current research are at a stage that we prove the concept that indeed we're using bioinspiration and the concept of architectures will create superior materials. And those materials we are using have similar properties than what the materials we find in the wasted materials. But still, we are using materials that are coming from standard factory. So it will be slightly different from what we can find from the wasted materials. So our next stage will be directly using the materials from wasted materials or using the recycled materials to try to create some materials that also have superior properties. And it will be difficult, as the materials we find in the wasted materials will be random, and it will pose difficulties for us to actually fabricate them. Our final goal is to actually build architecture materials which is high performance and low energy cost, and ready for high-value applications to build our world. And I think eventually we can build our world just like what nature does for billions of years. Nothing will be wasted in the future. Thank you.
Thank you, Zhen. So we have time as well for a few questions for Zhen. Everyone's too shy. Lauren, please.
So this composite material that you developed, is there a particular application for that you think that it could be use for something?
Yeah. Actually, when we do it for the applications, we sometimes for the building materials and also for some protection systems, like for body armor, and we also do for laminated glass, which is for windshield or for the glass curtain wall, something like that, which requires toughness and impact resistance. Yeah, that's the application we are aiming for. Yeah.
Can it protect our iPhone screens from getting cracked?
Yeah. Yeah.
Great. Any other questions for Zhen? Please,
Hi.
there.
Would you be able to recycle these new materials?
Yes, for sure, because like I mentioned, those wasted materials are pretty random. It's coming from everywhere. And if you use up, for example, those new materials, they're broken or something, and you put it in the garbage bin, it will be still the same way because we didn't change anything from its previous recycled or wasted materials. So we can still recycle them. That's for sure, actually. Yeah.
A last question? Thank you, Zhen.
Oh, thank you.